everyone, and thank you for joining us today. I'm Gosia Steiner, IBM Fellow and CTO of Hybrid Cloud Research. We are looking forward to a lively discussion about the latest cryptography research. Following the program, you'll have the ability to submit questions to an IBM speaker. We'll save the last few minutes for questions and try to get through as many as we can. And now let's talk about cryptography. Cryptography has been around for millennia. The first encrypted messages were disordered hieroglyphs carved on tombs in ancient Egypt. At IBM, we began exploring cryptography in the 1960s when IBM chairman Thomas Watson Jr. set up a cryptography research group. The group created an encryption method named Lucifer to protect the data for a cash dispensing system that IBM had developed for Lloyds Bank in the United Kingdom. In 1971, Lloyds Bank bought the code, and IBM worked to integrate Lucifer into its commercial product, the ATM. And today, cryptography remains a key part of IBM's business and a priority for IBM Research, one of the largest industrial research organizations in the world. In this session, we'll discuss three critical emerging areas of data privacy and cryptography: confidential computing, quantum-safe encryption, and fully homomorphic encryption. Each of these is solving a different piece of the data security equation. Let's start with one area of security research that companies today are actively using: confidential computing. Confidential computing provides hardware-level privacy assurance by encrypting data within a secure enclave that not even the cloud provider can view or access. In 2018, IBM became the first cloud provider to offer confidential computing for use in production. Currently, clients in the financial services, telecommunications, consumer healthcare, and government industries all use confidential computing capabilities from IBM. To share more, let's turn to Hilary Hunter, IBM Fellow and Vice President and CTO, IBM Cloud.
Thanks, Gosia. It's such a pleasure to be here today. To jump off on what you said, for IBM, our cloud strategy has always put the security and privacy of our clients' data at the forefront. We believe our clients, and only our clients, should have access to their sensitive data and to their data overall. And one of the ways that we're making that happen in technology is through confidential computing that you just described. These capabilities allow a company running workloads in the cloud or on premises to have full privacy and control over their workload, even though they don't necessarily own the infrastructure in the cloud context when the workload is hosted. IBM's been working with confidential computing now for around a decade, and we were the first to market, as you mentioned, with a commercially available solution in 2018. But we've worked since then with a handful of companies across different industries who are using our confidential computing capabilities to ensure that critical data can be processed with complete privacy. And we're going to talk about a few other key words in this space, but I'm delighted to have one of those clients here with us today and want to welcome Samuel Brock, who is the co-founder and CTO of DIA, which is an open source financial information platform. Welcome, Samuel.
Thanks for the warm welcome, and thanks for being able to be here. Welcome, everyone.
Wonderful, thank you. So Samuel, just to kick us off here, can you talk me through a little bit about DIA in the space that you're working in?
Yes, so we are a financial data provider providing data mainly on blockchain financial markets. So our main focus lies in decentralized finance and everything which has to do with on-chain reporting on different data sources. It's a very fast-moving space, and it's also a space where a lot of data is handled in a very short amount of time. So we need a reliable and scalable solution, while also we have obviously customers who are very decentralized and very spread out through many jurisdictions. And we want to show them that they can, that they can rely on our data and that our data is always protected with the highest level of integrity.
Yeah, it's interesting because I kind of hear you saying that data privacy is important to you because it's important to your end clients, right? It's part of being able to use something like confidential computing as part of the core value proposition that you then pass along to your clients.
Yes. So for confidential computing, I mean, one of the advantages in our space is that we don't have personal data in the traditional sense. So data privacy is not a concern in the privacy sense that people's data is concerned. So we have financial data; it's public data in the end. But what we care about a lot is data integrity and also the ability to be very sure that no one else can tamper with our calculations, with our database, so that everything is really in the secure enclave, but without the disability or without the problems we would have, for example, when doing it completely decentralized, which introduces a lot of costs, a lot of latency, a lot of complexity. So we try to get to the sweet spot of having decentralization only for parts where we actually really need it, and to use a centralized secure system when possible.
Yeah, I think it's such a great example because you've introduced that word integrity. And I think across many different industries, people understand that both privacy and integrity are important. There's high value capabilities, and then there's a lot of capabilities as you're dealing with across different industries where the integrity of transactions and the consistency and the ability to know and trust that process is important. And that applies to many different types of industries. That's great. Thank you. So I know you looked at a lot of different technologies. Can you just elaborate a little bit more on where you ended there as to why confidential computing versus general computing? How did you make that decision to leverage confidential computing and secure enclaves to establish that data integrity and privacy?
So with traditional cloud computing, let's call it like that, there's always the problem that we have to trust the cloud provider in some sense, that the data is, or on one side that the data in databases that are hosted there is not tampered with or not changed. On the other side, that also the computing itself, so the code which is run, is not changed. I mean, there's obviously protocols for that, so you can run it in a multi-cloud environment and then have it synchronized. But again, that introduces latency, introduces complexity on top of that. Then the question comes up: who controls the system on top of it? Is it running on-prem or is it also running in a cloud? Obviously, I mean, the cost of every attack will increase with every level of security you add. But also the potential benefits are very high because in our blockchain world, we're essentially working with programmable money. So if someone finds a bug or someone can find a way to access and to change our data, there's suddenly a very high monetary value. So there's a concept called cost of corruption, and this cost of corruption can be very it can be very, even for attacks which are very expensive, can be very beneficial to do them if you have like a monetary value directly coming out of the attack.
Yeah, and I know when we met earlier, we were chatting a little bit about some analogies that we've tried to help folks understand sort of those degrees of security and the cost of attack. As you said, in our daily lives, a hotel has video cameras outside and a security person at the front desk, and you use your key card to even get on the elevator. You use it to get into your room, but yet we all know there's a vault there that we may choose to additionally put very particularly sensitive things into in that room. And so it's always a matter of degrees. And for the type of work that you're doing, really, securing the integrity of transactions and data is that much more important to then make a specific confidential computing choice. That's great. Thank you. So I'm going to wrap us up here. Thank you so much for being with us today, Samuel. I think that was a great articulation of the practical application of confidential computing. And it's great to see your work live on our cloud and you all pursuing those opportunities in the market. So thank you for being with us today.
Thank you.
Thank you so much, Hilary and Samuel. Now that we have learned about the promise of existing technologies like confidential computing, and just how far we've come since the advent of cryptography, it's time to discuss what's ahead. At IBM, we believe that quantum computing is a large part of the future of computing, and currently have deployed more than 20 quantum computing systems. But quantum computers are really good at factoring large numbers. And the strength of today's cryptography depends on the difficulty of factoring. So clearly, quantum computing poses a potential security challenge. For more than 3 years, IBM Research, the National Institute of Standards and Technology, and the broader cryptography community have been examining new approaches to encryption and data protection to keep our most sensitive data safe from quantum computers. Let's learn more from NIST and hear from IBM researchers about our latest advances in this field.
Hello, my name is Dustin Moody. I'm a mathematician with the National Institute of Standards and Technology, usually known as NIST. I'd like to thank IBM for the invitation to come and talk a little bit about post-quantum cryptography and what NIST is doing to address this threat. Just an obvious disclaimer, I don't speak for the entire federal government, and because I'm speaking at an IBM event, that does not mean we endorse any products or anything like that. So over the past few decades, there's been a lot of research and work towards building what's called a quantum computer. A quantum computer would operate on a fundamentally different paradigm than our current classical computing technology that we use today. And if such a large-scale quantum computer were actually able to be completed and constructed, it would have a lot of positive applications because it has a tremendous potential for improving computational power. So there would be a very lot of positive applications in science and medicine and so on, but there would also be a consequence with regards to the field of cryptography. And in my area at NIST, we work on creating standards for cryptography, which tell the government and other organizations how they can safely use cryptography for their application needs. And it's been known for a while that with a large-scale quantum computer, that there are some attacks which would completely break some of the crypto systems which we use today. These are called public key crypto systems, and they are standardized in some of our documents at NIST. And even though we don't yet have such a quantum computer around, people are actively working on building one, you could already be under a threat of attack from one before one is built. And this is because somebody could take your data and information, which is encrypted using our current crypto systems, and they could just hold on to it. They can't read it because it's encrypted, but they can wait until a quantum computer comes along, and then they're able to crack into it. And you may not be providing protection that you hope for the amount of time that you do. Thus, it's important to already be thinking about this project and getting to work on making sure we can counter this threat. Now, all of this depends on when a quantum computer will be built, and the answer is nobody knows for sure. People are actively working on it, working very hard, making a lot of good progress. There are some experts who have estimated that it's possible that in 10 years, 15 years, maybe we might have one of these around. And so that's why NIST has been working on this project for quite some time. I want to emphasize that this is a field called post-quantum cryptography. It's to search for crypto systems which would replace the ones that would be broken by an attack from quantum computers. There's another type of cryptography that sometimes kind of gets lumped in with this because it has the word quantum in it, and that's quantum key distribution, or QKD. That's a different application, and I'm not talking about that. In 2016 at NIST, we published a short report explaining post-quantum crypto and talking about what we would be doing to work towards standardizing new crypto systems. In essence, we kicked off a large international competition. And the scope of that was for public key digital signatures and public key encryption, or key exchange algorithms. And we pledged to run a process that would be open and transparent to select the most secure and best crypto systems that came out of this process. Our criteria were number 1, security, and number 2, performance, besides a number of other characteristics that we hoped the algorithms that we received would have. And this was open to everyone. We received a large number of submissions, and we posted them on our website, the complete specifications, as well as a code that you could download and implement this. So internally at NIST, we are testing these, and we encourage people from around the world to evaluate them as well. We structured our process to be in a series of rounds, where at the end of each round, we would select a smaller number of algorithms to move on to the next round and for us to focus on. Currently, we're in the middle of the 3rd round. We have 7 finalist algorithms and 8 alternate algorithms that are currently being looked at. We expect towards the start of 2022 or so, we will select a small number of them to begin being standardized as the first quantum-resistant algorithms to be included in our standards for public key cryptography. We'll then put those out for public comment and hope to have the final version completely ready and published by around 2024. We definitely want people to be aware of the threat and what's going on with what's called post-quantum cryptography, and to be planning ahead. There will be a transition to these algorithms, and like any crypto transition, it's not going to be necessarily easy. And that's particularly the case here because we're dealing with algorithms that are a lot more complex in terms of the math they use and some of the characteristics that they have. They also have things like larger key sizes. So we, as much as possible, we're trying to prepare as much as we can and encourage others to do so. So we encourage companies and organizations to do an internal analysis of this, look at the crypto you're using. Is it threatened by quantum computers? Be aware of what's going on. And the sooner that you plan ahead, you'll be able to get ahead of the curve and not be left scrambling at the end. So once again, thanks for the opportunity to speak. And if you have any questions for me, the good folks at IBM will send those my way or give you my contact information. Thank you very much.
So good morning. My name is Vadim Lubashevsky, and I'm a research scientist here at IBM in Zurich. So we just heard Dustin from NIST talk a little bit about the importance of switching to quantum-safe cryptography. And he also mentioned that NIST narrowed down the selection list for the new standard to about 7 finalists. So I'll now talk a little bit about what IBM's role in this is and how we're planning for this quantum-safe future. So IBM has contributed 5 of the initial 69 schemes that started out in this standardization process in 2017. And 4 of these 5 are now among the 7 finalists, and the remaining 1 is an alternate. So we've definitely got some internal expertise in this field, and we're taking this transformation to quantum-safe crypto pretty seriously. So in fact, IBM has already incorporated quantum-safe crypto into a good number of its products. So for example, IBM Cloud and Red Hat OpenShift. And the cryptography that we've incorporated comes from a family of schemes that we submitted to NIST, which we call crystals. It's an acronym for a cryptographic suite of algebraic lattices. And these schemes derive their security from the fact that they're based on the presumed algorithmic hardness of something called lattice problems. And these lattice problems are mathematical problems that have been studied for many decades, and they seem to be resistant to quantum attacks. So luckily for us, they're also something that lead to very efficient cryptographic schemes. And what's more, and you'll hear an example of this later in this broadcast, is that the mathematics of lattices also allows us to construct things that can't be done in any other way. So they have benefits even beyond just quantum safety. So for these reasons, cryptography based on lattice problems really might become very important in the future. And I guess at this point might be interesting to ask, what are these problems? What do they look like? And how do they differ from classical problems upon which crypto now is based? So a classical problem, which maybe you've heard of if you know something about cryptography, upon which some of today's cryptography is based, is called factoring. So, I mean, there, for example, I give you a number, like, let's say 713. And what you're supposed to do is to find the 2 numbers, 23 and 31 in this case, whose product is 713, right? So for classical computers, this factoring problem is quite difficult, at least we believe it's quite difficult, when these numbers are big. So if the number I give you is 1,000 digits, I mean, I gave you a 3-digit number, so that's not hard, but if it were 1,000 digits, then the best algorithm on the best supercomputer would probably not finish for billions of years. Now, a powerful enough quantum computer, on the other hand, can solve this problem in a couple of hours, and this is where the problem comes in for security. So now, what are these lattice problems that we believe to be hard, even for quantum computers? Right. So the easiest way to explain what a lattice problem is as follows. So suppose someone creates a random list. For this example, let's just say it's 6 numbers between 0 and 100. And everyone knows this list. Me, you, the bad guys, everyone. I mean, in fact, if you were wondering what's behind me, that's the list, right? So here's this list, and then it's completely public. And what I do is I pick 3 of these numbers. I don't tell you what they are. And I write down their sum. So let's say I write down the sum, just, so you see what it is, 138. So now your job is to figure out which 3 numbers I picked, or what are the 3 numbers that sum to 138, right? So I guess there's no way for you to tell me right now. If you have the answer, maybe you can type it into the questions and the communications team will let me know if somebody gets it. No, I'll wait a few seconds. No? Okay. Well, anyway, it doesn't matter, right? I mean, the numbers were 28, 39, 71, right? So it's kind of hard, right? But I'm sure if you had enough time, you would figure this out. But it seems like, if we had more numbers, then for classical and quantum computers, this problem would be extremely hard. So if we had a list of, 1,000-digit numbers, then this problem seems like it would be hard even for quantum and classical cryptography, classical computers, right? And upon this problem, we can build very efficient and expressive quantum-safe cryptography. Now, as I said before, some of this cryptography is already in systems today. And it's not just IBM who is experimenting with the Crystals library. Other enterprises are too. And the software is open source, so anyone can go ahead and use it now. And so far from these experiments, we've noticed that the efficiency of the schemes is such that the end user won't notice any difference. So in fact, sometimes the new scheme is even faster. So the quantum threat is not an existential one for cryptography. We will have security. It's just that we need to do the work to switch over to different cryptographic algorithms. So I'd like you to walk away remembering just a few key points. So first is you do not need to do anything quantum to fight against a quantum computer. There are many normal mathematical problems which are suited to cryptography that a quantum computer most likely can't solve. And in the vast majority of cases, if today's cryptography is replaced with lattice cryptography, the end user won't see any negative effects. In fact, in some cases, it may even lead to a speed up. And third is there are many good reasons to start using quantum-safe crypto now. And these were mentioned by Dustin. For example, the most important one is, I guess, that your data now can be harvested and stored until a quantum computer is built, at which point it can be decrypted. So all confidential data from today can become completely leaked and insecure when a quantum computer is built. And to prevent something like this, because it's already efficient, there's really no reason not to start switching over to quantum-safe crypto now. And if you plan to do your switch, you can do it in an agile fashion, meaning you'll be able to later plug in any scheme that may eventually be standardized. So don't hard code your scheme in, but do the transition so that any scheme can be plugged in as a black box. And so thank you for your attention.
Thank you, Vadim, for giving us a peek into the insights of quantum-safe encryption and how it can protect us against threats from future technologies. We learned earlier that confidential computing is one way IBM is helping clients solve the challenge of maintaining the privacy of data in the cloud. It allows us to encrypt application data when it is in use. But what can be done to protect the data from the application itself? That's where the prospect of fully homomorphic encryption comes into play. Over the past 10 years, IBM has taken something so complicated that only a few people could use and turned it into 10 lines of simple code. Today, we are excited to share the latest advancements in this technology and how IBM is working to bring it from the research lab into early adoption by clients.
Our private information and data are being shared more widely than ever before. And often, we're the ones sharing it. We share our data in exchange for convenience and improved services. As long as our personal accounts remain untouched, we think nothing of it. And for most, giving up our personal information is required to interact in the digital world, both at work and to utilize basic everyday services. So how do we know our data is safe? Well, most of the sensitive data we share is encrypted. Encrypted data is useless to hackers and thieves, as it's translated into complex code or ciphertext that can't be read by humans. That's a good thing. But while encryption safeguards our data as it's being stored or transferred, the data must be decrypted or translated back into clear text to be processed. This provides a window of opportunity where your data is exposed, making it vulnerable to cybercriminals, privacy violations, and other misuse. IBM is combating this problem with fully homomorphic encryption, or FHE, which is changing the paradigm of security. It's a technique that enables computers to process sensitive data while it's still encrypted. For example, every time you hop in the car and fire up your phone's navigation app, the app needs to know where you are, where you're going, and any stops along the way in order to give you the best route. With FHE, the app could still provide those same directions, without the service behind it needing to see or save that information about you. Maybe you don't care about an app knowing your location. Maybe the convenience outweighs the risks. But what if this data was much more sensitive? like, say, healthcare records or your personal banking data, suddenly the stakes are much higher. The ability to apply AI, machine learning, and other computing functions to data without exposing more private information is the essence of what fully homomorphic encryption enables. First envisioned in the 1970s, an IBM researcher pioneered the mathematical framework to make FHE possible in 2009. But FHE was too slow for everyday usage because of the enormous computing power it required. Back in 2011, it took 30 minutes to process a single bit using FHE. But by 2015, we could compare 2 human genomes with FHE in less than an hour. And now through software and hardware advances, the time has come for companies to start experimenting with FHE. FHE will be a game changer for security in the hybrid cloud era, unlocking new business opportunities. With its ability to process regulated and sensitive data, FHE will drive wider enterprise adoption of hybrid cloud platforms, especially in highly regulated industries like financial services and healthcare. FHE could also impact mergers and acquisitions, where due diligence could be performed without violating the privacy of account holders, shareholders, and clients. Even airlines, hotels, and restaurants could utilize FHE to offer packages and promotions without giving their partners access to details of closely held customer datasets. But first things first, companies need to get their hands on this technology to begin developing real-world usages for FHE within their unique industries. With the launch of IBM Security's homomorphic encryption services, clients will gain access to both the tools and cryptography expertise needed to start building prototypes for their own FHE-enabled applications. Pushing forward on this new frontier of security is part of what positions IBM as the leader in hybrid cloud, all the while protecting the privacy and trust of clients and keeping your data safe.
Hello, my name is Eric Moss, and I'm responsible for strategy within the IBM Security Business Unit, part of which means getting technologies like fully homomorphic encryption out of the lab and into the hands of our clients. So let's first understand FHE. As you just heard, it's a unique form of encryption, and it's going to allow us to compute upon data that's still in an encrypted state. But to better understand that, let's first revisit some of the classical encryption models that we know well. We have data at rest, and this has historically allowed us to protect data that's being stored, whether on a disk or in a database. Then we had data in transit, and this allowed us to protect the confidentiality of data as we transmitted it between point A and point B over a network. What's been missing has been this ability to compute upon data while it's still encrypted, keeping the data in a protected state while a CPU can compute upon that data. So let's look at an example of this. Let's say we have an application, and that application needs to perform some type of statistical analysis on a data set. Well, in order for that application to do its job, the app first needs to decrypt the data in order to access it. Then it can perform its statistical analysis in the form of computation on that data. But the act of decrypting the data itself puts the data in a vulnerable and exposed state. With FHE, we now have the ability to actually keep the data encrypted, never exposing it during the computation process. This has been somewhat akin to a missing leg in a 3-legged crypto stool. We've had the ability to encrypt the data at rest and in transit, but we have not historically had the ability to keep the data encrypted while it's being utilized. This is being made possible by some of the same lattice encryption techniques and mathematics that you heard Vadim discuss. So again, let's look at why this is important to our clients and to businesses at large. First, let's acknowledge the fact that our clients are facing 2 really large forces against their business. The first is insecurity, but the other one is a business force. On the security front, companies are facing multiple pressures in the form of increased regulations, both industry as well as government regulations that are pushing for better privacy controls. The punitive fines and damages that go along with this are significant. On the flip side, though, these clients are looking at the business pressures that they're facing. They're looking to improve the use of their data, data as a competitive differentiator in the form of collaboration or monetization. And they also have an increasing reliance upon that data for their day-to-day operations. An example of this could be seen in the healthcare ecosystem. The healthcare ecosystem relies heavily upon collaboration between healthcare providers, insurers, clinical researchers, The ecosystem is quite vast, and they must have the ability to seamlessly provide high-quality services through data collaboration. But with that is also the need to provide trust and the ability to secure this data. And the ability to secure that data is paramount to their trust in the broader public's eye. In this case, FHE will allow us to secure that type of collaboration, extracting the value of the data while still preserving the privacy of it. Meanwhile, FHE allows us to provide a certain type of security that can follow the data. This differs somewhat from the confidential computing that we discussed earlier, as it's not reliant upon any type of special hardware. And it allows us to ensure that even data in untrusted environments where we have no control over the hardware can remain secure. So where are we today with homomorphic encryption? You heard IBM has been working on FHE for more than a decade, and we're finally reaching an apex where we believe this is ready for clients to begin adopting in a more widespread manner. It's been historically complex, not just in terms of the calculations that are performed on the data, but it requires a lot of computing power, and the skills and learning curve have typically been very steep for the normal client out there. But there's some good news here. Researchers have been working, as we discussed, to refine this process, making FHE much more efficient than it has been in the past. And we now have technologies that are going to allow our clients to more easily adopt FHE. And that becomes the next challenge, widespread adoption. There's currently very few organizations here that have the skills and expertise to currently use FHE. But IBM Research has been helping in this space by delivering not only open source and toolkits to help encourage that adoption, but IBM Security has recently launched its first commercial offering, IBM Fully Homomorphic Encryption Services, back in December. This is aimed at helping our clients start to begin to prototype and experiment with fully homomorphic encryption with two primary goals. First, getting our clients educated on how to build FHE-enabled applications, and then giving them the tools and hosting environments in order to run those types of applications. So how is FHE going to be used in the near term? As you heard, highly regulated industries such as financial services and healthcare will be some of the early adopters in this space. They have both the need to unlock the value of that data, but also extreme pressures to secure and preserve the privacy of the data that they're computing upon. But rather than just tell you about that here, let's talk to one of my colleagues, Omri in IBM Research, who can show us a demonstration.
Thanks, Eric. Working on FHE, we wanted to allow our customers to take advantage of all the benefits of working in the cloud, while adhering to different privacy regulations and concerns. What only a few years ago was only theoretically possible is becoming a reality. Our goal is to make this transition as seamless as possible, improving performance and allowing data scientists and developers without any crypto skills a frictionless move to analytics over encrypted data. In the demo I'm about to show you, we worked on a use case for such a regulated industry, the healthcare industry. In this demo, a hospital is sending private healthcare records to the cloud for analysis. Now, this could be done to analyze DNA for genetic issues, or as will be shown here, to alert regarding a possible risk for a certain condition. Now, prior to FHE, such analytics on the cloud were very challenging since the data had to be decrypted prior to processing. So this interfered with different regulations and privacy concerns. But now we are able to upload the data encrypted, analyze it while encrypted using a machine learning model which is in and of itself also encrypted, get the result of the analysis encrypted, and send them back to the hospital or the patient for decryption. So let's start the demo. As you can see, what once took hundreds of lines of code and advanced crypto skills is now accessible to data scientists, whom with less than a dozen lines of code, as you can see marked here, can leverage the capabilities of FHE. Now, if we run this code, give me a sec. Now, if we run this code, you can see that what was just 5 years ago would have taken a few hours is now processed in much less than a second. If you can see here, 0.069 seconds to be exact. Thank you.
Thank you, Omri. You've just seen 3 crucial technologies that are shaping the future of secure computing around the world: confidential computing, quantum safe encryption, and fully homomorphic encryption. These capabilities were born in IBM Research, and we are working with partners and clients, some of whom you have met today, to commercialize and integrate them into our everyday lives. Thank you for joining us today, and stay well.